So here we go. So far we haven't done work in this class. You know that? We haven't done work in this class yet. Today we're going to do work. Get it? I scare you? Oh, groans. Okay. So what is work? Work is like kind of like a total amount of force applied over a distance. And you know that just the real simple formula for work equals force times distance, right? Oh, well, I'm thinking of it. I still haven't gotten the Piazza thing going yet. As soon as I do, you'll know. I'll try to work on that today. Piazza is an online forum for posting and answering students' questions. And we'll be grouped with all the 272 students, okay? Not just our class. But I'm still working on that. Okay, so work is force times distance. We can investigate the amount of work to move an object. So work itself is scalar. It doesn't have direction associated with it. It's just how much work did you have to do. But force applied and displacement of the object, those are both vectors. Okay, so we've got a force vector, got a displacement vector, and then the resulting work is just a number without direction. That might make you think of something. Okay, so an example. A boy pulls his wagon with a force of 56 newtons at an angle of 39 degrees above horizontal for a distance of 8.1 meters. What's the work applied to the wagon by the boy? Or the work done, yeah, the work done by the boy on the wagon. Okay. So here's our force vector. We could put it here. 56 newtons. So 56 is not the vector. 56 is the magnitude of the vector, right? And then I'm showing the direction there, which we know is 39 degrees above horizontal. And then displacement, we could put as a horizontal vector like this. Its magnitude is 8.1. Okay, so first thing I want you to do is I want you to write the actual vectors f and d. Can you write the actual vectors f and d? Should be able to do that.
On the blue sheet?
No. Okay, where's Jake McLean? Where's Jake? Is that you?
Yes.
Did you get the f vector? No. Any idea about that? So when I say write a vector, what does that mean? What were you writing down? No, we got the magnitude. That's 56. So when I say write a vector, what does that consist of? Components, right? Components. So where's Gabriel?
Me.
Yeah, is that you? Juarez?
Yeah.
Yeah,
Okay.
sorry, I forgot your last name. All right, so tell me about F. What is F?
F would be 56 cosine of 39.
Okay.
That would be the horizontal component.
Okay.
And then 56 sine of 39, which would be the vertical.
Okay, you got it, right? So if we have components, right, it'd be the x component would be 56 times cosine of 39 degrees, and the y component would be 56 times sine of 39 degrees. Okay? Or you could write it in a unit basis form, which would be 56 cosine 39 times I plus 56 sine 39 times j. Okay, how about vector D? Where is... Ezrin? Ezra? That's you. Tell me. Did you get D?
No, I've not gotten that far.
All right. So what? When I say write the vector D, what am I asking you to do?
Write the components 8.1 would be magnitude, distance, 8.1, so the x value should be 8.1.
Okay, and the Y value?
0, or is it 39 degrees because it went up?
Is it going up?
So, is it just 8.10?
Is it just 8.10? Yes, it's just 8.10. The displacement vector, right? So all of the magnitude is in the x direction, so that's the x component, and then there's no y component, so 0. So if work is force times distance, does all of that 56 force contribute to the work here? No. So what part of that 56 newtons contributes to the force? Yeah. So yeah, the part that's in the same direction as the displacement. The part that's in the same direction as the displacement. Okay. So the part that's pulling straight up on the there's a part of that, the second component, that's pulling straight up on the wagon. That's not going to have anything to do with the work of him pulling it horizontally. Oh, sure. Okay, so all of the work that's done is going to be because of the horizontal part of the force. The vertical part of the force isn't going to contribute to the work done at all. Okay, so therefore, just if we use our force times distance equation, we can calculate the work. Force is how much force? 56 cosine 39. Distance traveled? 8.1. So only the horizontal component contributes. So calculating the work done, force times distance, would be 56 cos 39 times 8.1. And that turns out to be 352.5 joules, or Newton meters. In English units, it's foot-pounds. Foot-pounds is our work unit. In metric, it's joules, or Newton meters. Okay, so hopefully some bells have been going off in your head as we've been talking about this. So notice the work, what? It was the product of the magnitude of the force and the distance in as much as they were in the same direction. See that? We multiplied the force and the distance, but only in as much as they were in the same direction. So now fireworks should be going off in your head. What is this? This is dot product, right? This is dot product. Exactly what dot product is. So work is this really fundamental application of dot product. So going back and looking at that equation there, what did we really do? We took the magnitude of F times the cosine of the angle times the magnitude of D. And we said that was one of the ways to calculate the dot product, right? The product of the magnitudes times the cosine of the angle between them. What was the other way to compute the dot product? And so remember, there's two ways to compute the dot product. Multiply, yeah. Yeah, you multiply the like components together and add them. So let's try that. So also let's try that way. So we would just, what would we do? We'd looking up at the top vectors there, the dot product would be multiplying the like components and adding. So here's that. And what happens? You get the same thing, right? So if I take the x component, 5639, cosine 39, times 8.1, plus 56 sine 39 times 0, I get the same number, 352.5 joules. Okay, does that make sense? Does it make sense? Any questions? So this is a really important point here, that there are two ways to compute the exact same dot product. Okay? So just in any kind of problem, so lots of times I'll be watching a student work and they're trying to find, they know they need to find the dot product as part of a problem, and they're very fixed on, okay, I got to get the magnitude of one of them, and I got to get the magnitude of the other, and the angle between them, and then I can get the dot product. And they're doing all this work to do that, when all along, they had the components of both vectors. So you could just do it the other way. Just multiply the like components and add. So if you're trying to find a dot product, take the road that's most convenient with what you have. You don't have to. They both give the same number. Does that make sense? So both this and this, or I should say this. So this is the one way to do it, right? And then this shows the other way to do it. And that will always be true. That will always be true. They both are computing the same value, the dot product. So use what's most efficient in your situation. Yes, sir?
I may have missed this. Isn't that second value of 56 sine 39 degrees times 0?
Yeah. Okay, so questions on that? All right, so before we do projections, let's do a practice problem on your blue sheets. So if we could, so let's just leave the extras in the back, and then that way people coming in late can just pick one up in the back. But thank you for bringing them up if you brought them up. But just we'll leave the extras in the back from here on out. Okay, so suppose, and also come to class on time. Also come to class on time. All right. Okay, so we have some ramp like this, and say this is the point, I don't know, -6, -3, and 2 feet. So dimensions are in feet. So that's this point right here. And suppose that we're pushing a box up that ramp. Terrible box, but you get the idea. And we're pushing with a force of, a horizontal force of, so pounds, -12, -8, 0. So why is that pushing with a horizontal force? Why is that pushing? Why can I say that that force is a horizontal? Yes, sir.
Because the Z component is 0.
Yeah, because I'm not. So there's no force up or down, right? All the force is pushing back into the third octant there.
Also, it's for the Y, is that 8?
Yeah, -8. And then these are dimensions in pounds. So we're pushing horizontally on this box, and that's gonna move the box from the origin to this point on the ramp. Is the scenario setup clear? All right, find the work to push with that. If I'm pushing the box with that force from the origin up to that point, how much work is done? How much work is done? Does work equal? No. What does it equal? Times? Dot product. Distance? Distance is a scalar. Displacement, right? It's the force dot displacement. Force vector dot displacement vector. Which we showed explicitly on the first example, right? We showed exactly why that's true. Okay, we're going to move on. If you still need time to think about it, we're going to put it on hold and come back and think about it later. So now we're going to do projections. Projections. There are two types of projections of one vector onto another. The first is scalar projection, and the other is vector projection. So here we're going to be talking about the projection of B onto A. B onto A. So what is the scalar projection of B onto A? Well, it's kind of like the shadow of B on A. If you were to shine a light from here, let's hope the sun is never blue, right? Okay? If you were to shine a light down onto this, it would be like the shadow of B onto A. So we would drop a perpendicular like this, and then we're talking about that part of A. So the scalar projection is that length. So that's what we mean by the scalar projection. It's the length of the shadow that B casts onto A. Right? It's the length of the shadow that B casts onto A.
Is it always at a 90 degree?
Yeah. So it's always going to be right. So notice I'm not showing A as horizontal. It's always going to be the perpendicular projection of B onto A, like that. So what is that length? What does that equal? And the easiest way you could do it. What does that length equal? Yeah, so what about B?
Or magnitude B.
Magnitude of B times cosine theta. Right, so it would just be the length of B. Cosine theta would be that what the scalar projection is. Now, what's that a whole lot like? Dot product. So let's write out what dot product is. Dot product A dot B is?
BX
Component magnet. So what is it? It's the product of the magnitudes times cosine of the angle between them, right? The product of the magnitudes in as much as they're in the same direction, or to the degree that they're in the same direction. So now how can we write the scalar projection in terms of the dot product? So notice that our scalar projection is this thing right here. This part of it. So what does that equal? Dot product divided by magnitude of A. See it? So this right here is the scalar projection of B onto A, meaning the length of the shadow that B casts on A, right? The length of the shadow that B casts on A. Here, and so you could use dot product to find it, is what the point is. You can use dot product to find that length. Okay, so now what is the vector projection? What's the vector projection? The vector projection is that pertains to that same shadow, but now as a vector, right? So it's as a vector, there's that, what is that vector?
Be that.
So yeah, so let's see, I think you can do it. You can do it, right? So it's what? It's a vector in the same length, same direction as A, and we know what its magnitude is. So can you do it? Can you write down what the vector, see if you can figure it out. Take a minute. Everyone try to figure it out, and then I'll let you be first, sir. Where's Alexander Castro? Do you have any progress on this?
Yes.
Tell me.
From what we learned about getting vectors that were in the same direction,
Uh-huh.
so you can take the vector A
Uh-huh.
and put it over its own magnitude to get a vector that's in that direction, and then you just times it by the magnitude that we need to shorten the line.
Okay, so you said take the vector A and
Put it over the magnitude of A.
and what would that be?
That
Can you
would be
describe
a
what that is?
vector in the same direction of
Any direction in this? Any vector in the same direction? It's a particular vector in the same direction. Which one is it?
the vector A in the same direction.
But there's an infinite number of vectors in the same direction as A.
From the same starting position.
No, vectors are mobile, right? So this has a very, very important magnitude, right? Many of you know, yeah. So yeah, you're right. So but what is the magnitude of this right here? 1. That's the unit version of A, right? Yeah, so that's the unit version of A, and then you said?
Then you multiply it by the scalar projection that you got, because that
Yeah.
would be the magnitude of that.
Right. So then if we multiply that unit vector in the direction of A times the magnitude of our scalar projection, then we'll get that vector that has that magnitude in the direction of A. So I'll do that out in front here. So I'm going to do A dot B over magnitude of A times that. Okay, and so then we can kind of simplify that a little bit. What do you notice? Notice we got 2 magnitudes of A down here. So we can just pull that out and square it. So our whole scalar that we're multiplying A by is going to be the dot product over the magnitude of A squared. And then times A. So this gets us the right scaling factor to scale A to the vector projection of B onto A.
Do you still need to keep the magnitude bars? It's going to be squared.
Yeah, because you can't. Because what would it mean to square the vector A? So what would that mean, right? So no, so you're squaring a number, right? You're squaring a value. So yes, you need to keep the magnitude, because otherwise that would be implying that you're squaring the vector, and what does that mean? Okay, so you've got the formulas. You got some homework problems. There's one particular homework problem that doesn't prompt you to use this, but it's going to be very, very, very advantageous if you can recognize that this applies in that homework problem. Okay, so that's your hint. So you can do a rabbit chase in a roundabout way to solve this problem, but it'll be maybe 3 times the length of the solution that you would have if you applied if you recognize in the situation that projections apply, and you can apply either scalar projection formula or vector projection formula. It's going to make your solution very much more efficient. So be on the lookout. So even though it might not tell you to use projection, kind of have it as a tool at the ready to see if it, in a given situation, if it will fit. Okay, questions about that? So then let's talk about, with vectors, there's actually 3 types of multiplication. We've seen 2 of them. What's one of the types of multiplication that we've seen? Is that me? Isn't that noise? Yeah, dot product was one, and what was the other one? Scalar multiplication, right? So scalar multiplication, here's your fill in the blanks. Multiplies a what by a what and results in a what. Don't look at your notes. See if you know from your head. See if you know from your head. Where's Jonathan Kipperman? Did you get this?
Yeah, so multiplies a scalar by a vector and results in a vector.
He wants a scalar times a vector resulting in a vector. Agree with that? So what's the meaning behind this? When you take a scalar times a vector, this new vector is what? What kind of thing do you get? Yeah.
You get a
Oh,
vector
good.
of just a larger magnitude.
Larger magnitude.
It's proportional to whatever you multiply by.
Okay. Other ways to say it? Yes, sir.
Scaling a vector.
Yeah, it's exactly scaling. So it's like, yeah, magnifying or shrinking the vector, maintaining its direction, unless the scalar is negative, and then your direction in the direct opposite way. Okay, so yeah, scalar multiplication scales your vector. It scales it, right? It magnifies it or shrinks it, and it might flip it around the other way if it's a negative scalar. So I'll let you fill in the blanks there. Okay, the next type of multiplication we've seen is dot product. Go. Multiplies what by what and results in what? You want to answer? Sure, go ahead. He wants vector times the vector giving us a scalar. People are nodding, okay? And where's Jacob Smith? Jacob Smith. Yes, sir. Meaning of a dot product. Do you remember what it is?
Well, it shows you how much the vectors are in the same direction.
Okay. But that actual value that we get, so yeah, it has to do with that, whether being in the same direction or not, but that actual value is what? Yeah.
The magnitude of the new vector created by the two.
You're not creating a new vector. Yeah.
Is the product of the magnitudes as long as the two vectors are in the same direction?
Okay, so yeah, so the number is first and foremost like a product of their magnitudes. It's like a product of their magnitudes. But then that's adjusted for how much they're in the same direction, right? So only in as much as they're in the same direction, or to the degree that they're in the same direction. So then when the vectors are actually pointing in the same direction, you get the product of the magnitudes. When they're orthogonal, what is that?
The knocking noise? It's
Yeah.
outside. There's
Oh,
a
it's
little-
not?
There's a little line from there, but there's something being knocked around out over there.
No, it sounds like a keyboard.
Yeah, it sounds like I'm
from another classroom.
another classroom?
Probably.
Okay.
I mean, it's not you. It's
I know, there's nothing
touching.
touching this keyboard up here. All right, okay. So, yeah, so to what degree are orthogonal vectors in the same direction? There's no part of the one in the same direction as the other. So they're going to get a zero dot product when they're orthogonal. Okay. All right, the last one is the cross product. Cross product multiplies a vector by a vector and results in a vector. So here's the third type of multiplication we see with vectors. This type is you do a vector times a vector, and you get another vector. So I got another worksheet. Unfortunately on gray paper. Not intended. That's the way it goes sometimes. Just pass left and right once we get to the back. So again, you're going to start by doing the first 7. Do the first 7. So you're going to draw 3 vectors. I'll put the instructions on the board. So for the first 7, you're given an equation, A, so I'm giving you A and B and the resulting cross product vector. Okay? You're going to sketch all 3 vectors and make sure you're noting which one is the result, the C, okay? Make sure you result. Which one are the 2 starting vectors, which one's the result, okay? And then you're going to make observations and conjectures about the magnitude and direction of C relative to vectors A and B. Okay? So let's just do that much first, not go on. So do the first 7. Let's see what you came up with. So this is a little bit a trickier beast than dot product. Okay? Dot product has this kind of clean result. This is harder, but you know, if you shoot for the moon, you might make it out of the atmosphere, right? Okay. So flip over the page. All right, what did you notice when the 2 original vectors had the same direction or opposite directions? And that just means parallel. Parallel vectors are exactly the same direction or exactly opposite direction. What did you notice about the cross product? It's called the 0 vector. Okay? 0, 0, 0. That's called the 0 vector. So, what's its magnitude? What's its direction? There is no direction, right? It's a point. It's just like a point. So there's no direction associated with the 0 vector. Okay? All right, so now let's talk about magnitude. What did you find if you had orthogonal vectors? Did you find something about the magnitude of the resulting vector? What's that?
It's the multiplication of the 2 vectors' magnitudes.
Right, it's the product of the magnitudes. So this is kind of like, so this is similar to dot product. With dot product, we know that the dot product was the product of the magnitudes, and if they were in the same direction, we got the maximum. We got the actual product. But here, when do we get the actual product of the magnitudes? To be the magnitude of the dot product. Right? That's this case when they're orthogonal. So, when they're neither parallel nor orthogonal, how could we characterize the magnitude of the resulting vector of the cross product? How about anyone new? Someone from the back? Did you come up with? So we've got two vectors that are neither parallel nor orthogonal. What about the magnitude of the cross product vector? Yeah. Yeah.
Considering that when they're orthogonal, you have a maximum magnitude.
Right.
When they're parallel, you have least magnitude.
Right.
Then there's something to do with the sign of the angle.
So you do the sign of the angle. Okay. Well, there's another hand back here. Yeah. Go ahead.
If there is an obtuse angle between the two vectors that are being cross-multiplied, you can have a larger cross-product vector.
Okay. It's not necessarily obtuse is going to be larger versus acute, but yeah. So it has to do with the sign. So it's kind of not the opposite, but the complementary case to the dot product, right? So the magnitude of the cross product is the product of their magnitudes in as much as they are orthogonal direction, right? So our best situation for cross product is when they're orthogonal. We get the biggest cross product vector. And then as they come together or come apart, like as the angle becomes larger or becomes smaller, then what happens to that cross product vector? It shrinks to 0 when they're parallel. Either way, whether it gets more obtuse this way or more acute this way. And so that's a function of sine, right? That's a function of the sine angle, sine of the angle. Okay, so what about the direction? Okay, so now that was all talking about the magnitude of the resulting vector. So what about the direction of the resulting vector when you have non-parallel vectors? So did you come up with some kind of scheme for that? Yes, sir. Okay, this is the most important thing. Okay, whenever you take a cross product of two vectors, your third vector, the resulting vector, is orthogonal to both of the first two. In other words, it's orthogonal to the plane created by the two original vectors. So skipping to to that last one here, we got 0, -2, 0. And 4, 0, 1. Okay, so I'm cross-producting 0, -2, 0. So the resulting, and this is what, 4, 0, 1, the very last one on there. So that makes a plane. What that plane is what? It's angled up from horizontal a little bit, coming out at you, right? It's coming out at you a little bit on an up incline. Do you see that? Because of that 1z of that second vector. So where would the vector be that's orthogonal to that plane, or orthogonal to both of those two vectors? So first of all, would it be positive or negative x, the orthogonal vector to both of these? Positive x, leaning forward like this? Be negative, right? Be leaning back, right? If that ramp is coming up at you, then the orthogonal vector is going to be leaning back. Now the question is it going to be positive z or negative z? How do you know? Because both. Yeah. So I guess if x is negative, it would have to be positive. So the question here is that here's this line that's orthogonal to that plane, okay, of those two vectors. So how do we know? Does it point up and back into the screen, or down and coming out of the screen? Both of that whole direction is orthogonal to the plane. You see that? How do we know which way it points? How do we know which way it points? It's called the right-hand rule. The right-hand rule. Here's how the right-hand rule works. You take your fingers and you point them in the direction of the first vector in such a way that when you curl your fingers, you're curling your fingers towards the second vector. So if you notice, there's two ways that I could point my fingers in that direction of the first vector. I could point them this way, or I could point them this way. So which one of those two ways, A like this or B like this, when I curl my fingers, curls towards the second vector. So does this curl toward the second vector, or does this curl toward the second vector? First or second? First. So this is the way I want to point my fingers, so that I can curl my fingers towards the second vector. Now my thumb is going to tell me the direction of the cross product. So notice there's two ways I can point my hand down that first vector. So I'm going to pick the way that when I curl my fingers, curls towards the second. And now my thumb is pointing in the direction of the cross product. So which way is it? Up and back into the board, or down and coming out of the board? Up and back, because I'm going to position my right hand this way, curling towards that first vector, means my thumb points up and back into the board. Now, what was that magnitude? So here's going to be the cross product, going back into the board, right? Like this. So what's the magnitude of that vector? What do you notice about the first two vectors? They're orthogonal, right? Those are perpendicular vectors. Therefore, this magnitude will be product of the magnitudes. Product of the magnitudes, right? That was our best case scenario for cross product. When they're orthogonal, we actually get the product of the magnitudes. So what's the product of the magnitudes? This magnitude is 2. This magnitude is radical 17. Radical 17. So is this 2 radical 17? Product of the magnitudes, 2 times radical 17. And we know that direction is going to be such that this is perpendicular like this, and this is also perpendicular like this. So that blue vector is perpendicular, orthogonal to both the original vectors. Or it's orthogonal to the plane made by the original vectors. Okay, so we're seeing some things form here. We know that the magnitude of the cross product is equal to the magnitude of the products of the magnitudes in as much as they're orthogonal. So it's going to be times sine theta. Well, that's the magnitude, right? That's the magnitude. We know the direction of A cross B is according to the right-hand rule. Okay, and so then the last thing is we need an algorithm for computing this vector using components. Okay, so how do we compute the vector using components? Well, it's actually the determinant so computing the components of A cross B. What we do is we find the determinant of the 3 by 3 matrix where the first row is our unit basis vectors. The second row is our vector A, so that was what? 0, -2, 0. And our third vector is B. So if you apply the determinant algorithm to this matrix, the matrix whose first row is ijk, whose second row is abc, and whose third row is, whose second row is a, and whose third row is b, the determinant algorithm will give us the vector that's the cross product. So there's different ways to do the determinant. Here's the way that I like the best. The way that I like the best is to rewrite the first two columns again. If you have a different way to do the determinant algorithm, go for it. There's different ways. This is the way I like. Rewrite the first two columns again, the I column and the J column. And then we've got three diagonals down to the right. We're going to multiply down those diagonals and add those. And then there's three diagonals down to the left. We're going to multiply those together and subtract those. Does that make sense? So, three diagonals. I times -2 times 1, j times 0 times 4, and k times 0 times 0. We're going to add those together, and then we got three diagonals going this way. K times -2 times 4, I times 0 times 0, j times 0 times 1. We're going to subtract all those, and that's going to make a vector when we do that. That's going to make a vector in the unit basis form, right, with the I, j, and k. So what do we get? -2i. That's that first diagonal. That's this one right here. 0j, 0k. That's going down to the right. Going down to the left would be -8k, but we're going to subtract that, so plus 8k. Zero I, 0j. What's the vector? -2, 0, 8. Does it agree with what we came up with, that blue vector? -2, 0, 8. It looked like something like what we came up with. Yes, right? It has some kind of shallow negative x coordinate and a big z coordinate. So that matches that blue vector that we had. All right, so questions? Did I lose you? Yeah.
Where'd you get the 8k from?
So we went down to the right on three diagonals that go down to the right, and then we go down to the left on three diagonals. So that first one was this right here. K times -2 times 4.
Okay, yeah, okay, nice.
And then we're going to subtract that, so it'll be positive 8k. And then we have I times 0 times 0, j times 0 times 1, but those are both 0. Other questions?
Say it again.
All right, so I'm going to just...
Down to the right 2 times?
3 times. There's 3 diagonals down to the right and 3 diagonals down to the left. So here's the 3. So boom, 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 and 3 more booms. Boom, boom, boom. The ones that go down to the right, we're going to multiply down those diagonals and add all those. The ones that go down to the left, we're going to multiply and subtract those. So the only ones that gave us non-zero results were this one here, I times -2 times 1. So there's my -2i, or -2x component. And then coming down to the left, I got a non-zero one here. K times -2 times 4, which gave me -8k, subtracting positive 8k. And then that vector agrees with what we came up with. I can stick around for a minute and answer any questions. I'll leave this up there. If you would please, once again...